Hello everyone, and thanks for joining. My name is Neşet Ünver Akmandor, and I'm going to present our paper called Deep Reinforcement Learning-Based Robot Navigation in Dynamic Environments using Occupancy Values of Motion Primitives. Autonomous navigation in dynamic environments remains a challenging problem in robot motion planning. In recent years, DRL-based approaches have shown remarkable results on this subject. Through observing their environments via sensors and training by task-specific rewards, robots are able to navigate in unknown areas while avoiding dynamic obstacles. Adopting end-to-end network methodology, some works utilize raw sensor data to represent their observation space. However, without any proper filtering, it causes huge observation space which requires large neural networks with long training times. Instead of directly using the sensor data, some researchers focus on defining neural network modules to encapsulate the necessary observation data. In that case, both modules, sensor data abstraction and the agent's policy, needs to be trained hierarchically, which results long training times as well. In our work, we propose a method that enables fast mapping of the occupancy data into the occupancy values of robots' motion primitives in 3D workspace. Our navigation framework starts with an offline process where we sample discrete set of trajectories given robot kinematics. The online process assumes three inputs. First, sensor data such as laser scan and/or depth image. Second, localization and robot odometry. And third, navigation target. At each time step, the local occupancy map is updated by using the most recent sensor data and localization info. We calculate our target observation as the concatenation of robot's distance and yaw angle to the goal. To benchmark our proposed occupancy representation, as we call Tentabot, we use raw laser data and its two different processing methods from the literature. Our action space is formed by a discrete set of lateral and angular velocity values, which generates our sample trajectories. Similar to state-of-art methods, we also include the action in previous time step into our observation space. For the analysis, we perform the training using the three different neural network architectures. For the first one, we use only fully connected networks to map the observation space to the action space. Based on the observation data structure, the second and the third one use 1D and 2D convolutional neural networks respectively, with a fully connected network following them. We design our reward function to supervise the robot to reach the goal and avoid collision with obstacles. To reduce the training time in which the robot might inefficiently spend exploring its state space, we also define a negative step reward. To train our robot in ROS Gazebo simulator, we create 5 different environments changing in area size, number of static obstacles, and dynamic agents. At the beginning of each training episode, the robot and target goals are initialized at random position inside the yellow areas of the respective map. Similar to other works, we use hierarchical training methodology to improve the convergence rate compared to training only within a single complex map. Our training benchmark includes 7 different approaches which differ from each other by their occupancy data structure. We train 200K time steps in each environment. The training results show that the learning rate of laser image and ring representations are too slow comparing our counterpart. Since their cumulative rewards couldn't reach positive values even after 200K time steps in the first map, we do not proceed with their training. In terms of overall rewards, the representations which use CNN networks achieve higher scores. However, between our representation and their laser counterparts, there is no clear winner. Although the laser 1D CNN FC converged faster than our approach, we should point out that our representation had an important disadvantage against its laser counterparts when we collected this training data. Although we use same network parameters suggested by other papers, our occupancy space had 15% more values, which caused less learning within the same amount of training time. As a future work, we will address this issue by optimizing hyperparameters, such as number of layers and number of neurons in these layers, for each of these different data structures. To compare the navigation policies trained by different approaches, we performed simulation tests in 5 environments. They include overtaking an agent moving towards the goal and moving towards the robot, avoiding agents which are crossing, navigating in complex static environments, and same environment with random dynamic agents. Based on the training results, we performed navigation tests using 4 successful training policies and 2 reactive planners. We compared their performance in terms of navigation success rate. To test the robustness of each policy, we performed the same test 10 times and calculate their mean values. When we compare Tentabot FC with its laser counterpart, we observed that Tentabot FC is superior in 4 out of 5 testing environments. Similarly, when we compare Tentabot 1DC and NFC with its laser counterpart, again, the results show that our approach performs better, especially in novel environments. Overall, the robots trained with our approach have higher navigation success than other methods, including reactive ones. We also test feasibility of our approach on an actual robotic system. We publish various goals in multiple environment settings with static obstacles, dynamic obstacles, and crowd. In real-world experiments, our robot reached the goal every time, even it has some physical contact with dynamic agents, but without colliding any static obstacle. Thank you for your participation and interest in our work. I would like to conclude my presentation with some photos which were taken in Japan long time ago. They all remind me priceless memories, and this conference has already joined to them.